All right, welcome to session 7 of the program, where we learn how to move, and I'll be the session chair. So I'm not in animation, but I've been in graphics long enough to witness the incredible progress there has been in this field, from the initial keyframing to very reactive and natural-looking motion. Nevertheless, as we've seen Monday during the keynote in particular, animation remains a very difficult challenge. We've seen also that learning techniques will likely help. And in fact, this morning, yes, we will see two such methods. So the first paper is about a very difficult challenge regarding the simulation of garments. And the paper is entitled Efficient Deformation Learning of Varied Garments with a Structure-Preserving Multilevel Framework. And the talk will be given by Takahashi Kanai, who is a professor in the Graduate School of Arts and Science at the University of Tokyo. His research interests include geometry processing, physics-based animation, and recently AI for animation in computer graphics. Thank you.
Thank you for your introduction. So, hi, my name is Takashi Kanai from the University of Tokyo. I'd like to talk about my recent research entitled Efficient Deformation Learning of Varied Garment with Structure Preserving Multilevel Framework. This is a joint work with Tianxin Li, Lui Xi, Zuhi Li, and Kinzo from the Beijing University of Technology. Okay. Cross animation is a fundamental topic in computer graphics, aiming to generate realistic garment deformation effect. And this is crucial for applications such as virtual try-ons, video games, and films. Achieving a realistic simulation of how these garments behave is essential for enhancing the overall quality of the animation. And considering the importance of realistic garment simulation, it is crucial to recognize that garment deformations are highly nonlinear. The complexity comes from various factors. First, the type of garment significantly affects how it changes shape in animation. For example, a jumpsuit and the dress each behave differently. Moreover, the body shape of the characters and the character motions also greatly influence how the garment deforms. And moreover, the body shape of the character and these factors are linked, making precise modeling of crossing a different job. Physics-based methods provide high-quality result by formulating the deformation process within a simulation framework. Yes. However, these methods are usually computationally expensive and are often avoided in interactive applications. Additionally, since these methods do not use existing data, achieving a high level of automation becomes challenging. On another front, researchers are using geometry-based deformation theory to investigate how neural networks can automate the creation of skin weight and blend shapes. And while these methods provide relatively fast and plausible results, and they still face limitations in accurately producing folds and wrinkles. Recently, learning-based methods for simulating garment deformations have gained popularity in the field. Researchers are exploring how to include realistic details and movement when dressing up parameterized human models, with the goal of making crossing animation look even more lifelike. Some of these methods use conventional neural network structures such as fully connected layers, which allows for the quick generation of deformation results. However, they require data to be transformed into flattened vectors, a process that often results in the loss of relational structures within the data. As a result, these methods can handle meshes that have arbitrary topology or varying number of vertices. With the widespread use of graph learning, graph neural networks are now being applied to mesh deformations. They excel at handling structured data and can generate well across different simulations. However, traditional graph learning-based approaches often encounter challenges, including learning difficulties and overly smooth results. Okay. Motivated by existing challenges, we focus on satisfying several aspects simultaneously: generalization, realism, and efficiency. To this end, we propose a unified multi-level framework that is designed to meet all these requirements efficiently. Our contribution can be summarized in three key aspects. First, we design strategies for generating description of deformation-related information, making it easier to apply the model to scenes with various objects. Second, we present structure preserving pooling and unpooling method for garment deformations. This method helps spread information throughout the mesh, improving the quality of the deformations. Finally, we perform an attribution analysis for evaluation, showing how the proposed strategies impact network decisions and directly influence the behavior of garment mesh node. Briefly, our project begins with an initial garment mesh, SMPL human body model, and a sequence of pose histories. Our objective to develop a robust garment deformation framework. This framework will be trained to accurately map these input to temporal skinning weight and blend shapes for the garment. The final dynamic deformation will be achieved by applying the temporal skinning weight and blend shape to the garment mesh, thereby effectively capturing the realistic deformation over time. Our object of deformations are 3D garments, which are inherently complex because of their varied shapes and structures. To handle this complexity, we construct a graph for the garment mesh. In this graph, X represents the feature set of all vertices, including position, normal, and distance to the all-body joint, and E represents the edges. Then, we employ a garment graph encoder to transform these graph features into the latent representation. While we include local information within the garment graph, it is crucial to also consider the overall content of the garment as important. To distinguish between different garment styles, our method uses the affinity matrix of the 3D mesh for this purpose. As shown in the figures, there is a clear similarity between the affinity matrices of the dresses and jumpsuits. Thus, we use eigenvalue from the affinity matrix as a style descriptor and process them through a garment style encoder to create style-related cues. Another crucial factor influencing garment deformation is the body shape. We introduce a joint vertex distance feature to describe the shape. These shape features are then forwarded to a body shape encoder to generate body-related cues. By integrating the garment graph with style-related cues, we combine information from the both the body and the garment to create a comprehensive graph representation. For motion sequence, we employ two temporal encoders to extract features. These features are then combined with the integrated graph to generate the skinning weight and blend shape, which are applied through skinning to achieve the desired result. Here, as blend shape is more complex and personalized, we employ an additional multi-level processing module to generate them. And graph pooling naturally contributes to the rapid diffusion of the vertex information. However, we cannot directly use existing graph pooling strategies for the garment deformation task, as the pooling strategies from the other applications do not always focus on preserving structure. For the garment mesh graph, its structure remains unchanged during the animation. Based on these considerations, we use the garment graph information itself to design the pooling and unpooling processes. Specifically, we begin by selecting a seed vertex based on the eccentricity of the graph. This one also. And during the mesh traversal process, we remove vertices that have an odd geodistance. Then we add edges that maintain the original connection relationships, ensuring structure's integrity. Each pooling operation generates a more compact representation of a graph. Our unpooling process starts by identifying neighbor relationships from the set of removed and coarsened vertices. We then calculate the weight and integrate the coarse vertex features back into the final graph. Finally, we normalize these weights to apply them to reconstruct the features of the removed vertices. In summary, we use the unit style to build our multi-level processing module, which include 2 pooling and 2 unpooling stages. We evaluate the structure preservation abilities of different pooling strategies. Some methods might result in excluding vertices in certain areas, which could compromise the structure's integrity. In contrast, our method based on simple principle managed to simplify the mesh while keeping the overall structure intact. This ensures that the key features of the garment mesh are maintained throughout the deformation process. And we also present qualitative deformation result. As shown in the video, our method efficiently captures the global features even in unseen scenarios. This ability is crucial as it assists the model in generalizing to test data and in producing reliable deformation predictions. Additionally, we compare the result between single-level and multi-level processing. Single-level processing does not involve pooling and unpooling layers. As demonstration in the video, our deformation result consistently show superior quality. Our method can generate larger wrinkle areas on test garment without without artifact, showcasing the advantage of our multi-level approach. By testing various garment, body shapes, and movement, our method can consistently produce satisfactory results. Next, we further enhance the interpretability of our result. We integrate attribution calculation, a technique from neural network interpretability research, into our method. So, This attribution method identifies key vertices in the input graph that influence the output. Vertices that impact deformation are highlighted in a heat map showing their attribution values. In our framework, these vertices have a broader impact, leading to more comprehensive deformation across the garment. We further explore the impact of distinct body shapes on the deformation of the same garment. It's clear that the detailed fold in the garment closely matches the body shape. Moreover, the attribution result displayed in the second row illustrates that the field of influences affecting the vertices varies across different body shapes. We compare our method with other state-of-the-art learning-based approaches. Our model establishes a well-rounded balance between model generalization, deformation quality, and efficiency, thereby demonstrating superior overall performance. This not only shows how effective our approach is, but also emphasizes its great practical value. To conclude our work, we first produce a To conclude our work, we first propose a comprehensive representation of the garment that efficiently includes deformation cues from various information sources. We then present pooling and unpooling strategies designed to preserve the graph structure and create a multi-level processing module to ensure effective feature transition. Lastly, we enhance the interpretability of our approach with attribution analysis. Our proposed method works in real time, showing strong generalization abilities and can approximate dynamic deformations with precise detail. There are also a few limitations of our method. First, our model has not yet resolved the issue of self-collision, which may occur in extreme poses. And secondly, our method currently does not consider material-dependent parameters. In the future, these parameters could be included as one of the input features to enhance the model's accuracy and applicability. Furthermore, we currently use SMPL bodies as human models. Future work could explore methods to adapt our approach to different human model types, expanding the versatility of our technique. Thank you for your attention.
Thank you very much. Are there any questions in the audience? Yes? I think so.
Thank you. Thank you for the presentation. And I understand how difficult it is, because in my team, we are now exploring the use of graph neural networks for simulating garments and the dynamics. And I saw that you, in one of the slides, pointed to the problems of the graph neural networks. Maybe at the beginning. So
Yes, sir?
No, it was before. But anyway, I just don't want to take a lot of time. What I wanted just to tell you that I will be very interested in talking with you about your experience on that, because we are struggling. We have an additional, let's say, constraint, which is that we want to run a real time on mobile, right, inside of a game. So we only have 3 to 5 milliseconds, right, to do everything, right? So it would be great if we could talk and maybe even collaborate on that, right?
Thank you. So this software develops in the China side. So I don't develop software, but I don't have the right to make the code to give you. But but collaboration is welcome. Yeah.
Thank you. Any other question? Yes, in the back.
Hi, Tomer from New Jersey Institute of Technology. Great talk. I just have a high-level question. Maybe I missed it. Can you maybe say what the advantages of these neural methods are compared to like traditional, like interactive computing of elastic materials, like, you know, position-based dynamics, NPM? Because it seems like there's a lot of restrictions here with the cloth and kind of fixing the cloth, and like there's not too much deformation. So I'm just wondering, like, what are the advantages here compared to classical kind of methods?
So in application, so we currently, so we think this method is practical, but we have not yet developed the actual application. So then So I hope this and I think so, to my understanding, so, and the physics-based method, so currently is limited use for a real-time application. And in this method, we can you can so predict the movement of clothes, and practically and like the physics-based approaches, I think. So and this answers your question. Sorry.
All right, thank you. I think the
Please
speaker will
discuss
be
after.
exactly.
Okay.
Thank you very much. We'll have to move to the next talk. So thanks the speaker again. Thank you. All right, so the second paper of the session focuses on crowd simulation. So, of course, crowd simulations are very important for games, for instance, which are populated with many NPCs. So I'm looking forward to see more realistic crowd simulation. And the paper is entitled Learning Crowd Motion Dynamics with Crowds, and the talk will be given by Bilas Talukdar. Bilas is a PhD student at the New Jersey Institute of Technology with research focused in computer graphics, crowd simulation, reinforcement learning, and physics-based simulation. You can start.
Yeah, thank you. Thank you everyone for being here. I am Bilas Talukdar, and my other authors are my colleague, PhD colleague Yanhao Zhang, and our advisor Thomas Weiss. So before going too deep into the problem, let's get an overview what the topic is about. So this is one of the pedestrian street crossing in the Japan, which is Shibuya Street Crossing, and every 3.5 minutes, 2,500 people crosses the street. So as you can see, there is a lot of individual navigation preference and individual navigation decision, and that makes overall dynamics very complicated. And our goal is to simulate such kind of complex interactions visually, realistically, and collision freely. Sorry. So computing multi-agent dynamics has applications in entertainment, maybe in animations or movies where we want to create large virtual crowds, and also in robotic crowds we want to move them smoothly, and also in cases of extreme situations like fire or maybe any other unwanted occurrences, we want to move crowd very safely. So this has application and also in extreme situation and urban planning. The challenges in computing multi-agent dynamics are to ensure collision-free and realistic motion, because as you can see, there could be there are definitely multiple number of crowds in the scene, and each has individual preference of moving. Someone may be running, someone may be walking slowly, and that makes the the overall dynamics very complicated. So there are both rule-based and learning-based method in crowd simulation. And here are some examples of typical state-of-the-art rule-based crowd simulation method. Though they are very good in generating believable crowd behavior, navigation behavior, but still they sometimes fail to generalize in different diverse scenarios, and they may lack anticipation also. As a cause, they get stuck in the middle, and this is not desired. So the classical rule-based crowd simulation method, one of the disadvantages of these methods is we need user-defined rules of navigation, and these rules of navigation typically need to be modified for each individual scenarios, and which means they lack generalization in their method, and also they might be able to lack anticipation in some cases, and their ability to capture the pedestrian behaviors is limited to a certain capability. for this, researchers has been recently concentrated on learning-based method also, where deep reinforcement learning is one of them. So the way deep reinforcement learning works is agents in the environment gets observation as input from the environment, and they take certain action to the environment, and based on the action, environment gives them either positive or negative reward, and based on this reward, agents ultimately learn whether they need to repeat the same action in the next time step or not. So by iterating through this learning learn and error process, they eventually learn how to navigate to a crowd space. So one of the advantages of these learning-based methods are we don't need any manual rules for moving the crowd. They can learn trial and error, and also they can capture a variety of actions given minor differences in input state. And presence of stochasticity in these methods being kind of probabilistic motion in the crowd space. So let's see some state-of-the-art reinforcement learning-based crowd simulation method. Crowd simulation by deep reinforcement learning by Jade and Lee, one of them, where they propose a reward function to move crowds in different novel scenarios. But as you can see in their results, they still have some limitation, like there is sudden frequent changes in their trajectories and sudden orientation changes, which doesn't look good and is not desired in crowd simulation. And also configurable crowd profile is also another state of the reinforcement learning method, where the authors design a dynamic reward function which can be changed during the training. But in their method also, we can see in case of goal seeking and collision avoidance, the agents avoidance behavior is not as smooth as expected. They kind of wait and then resolve the collision eventually. So the summary of the prior works is the typical reinforcement learning for multi-agent results in a game-like movement, which doesn't necessarily resemble the pedestrian's movement. And most importantly, none of the previous methods considered simulating agents in a manner that multiple other viewers considered natural. So from that perspective, we have our contribution is twofold. One is we offer a novel we propose a novel deep reinforcement learning method with novel reward term which supports natural crowd motion, and also we use position-based dynamics as a training environment. As the second part, we propose a novel crowd-sourced Bayesian approach for selecting optimal learning parameters of the reinforcement learning. So before going too deep into the problem, so I will show some results of our method where we demonstrate how generalizable our trained policy is. So as you can see in this circle method, the agents are basically tasked to reach their goal, which is the antipodal position of their circle. And as you can see, our agents using our method can reach to the goal smoothly and collision-free, and showing predictive crowd motion. And also in other scenarios like obstacle, hallway, quad, and corridor, agents locomotion behavior is predictive, smooth, and collision-free. Notably, none of these scenarios are seen by our agents during the training. So basically, we train our policy in different scenarios, and we show how generalizable our policy. So this is one of the desired aspects in crowd simulation. We want to see how robust our method is, how your trained policy can be generalizable in different unseen scenarios, and our method is good at that, as you can see. Let's go deep into the reinforcement learning part. So we represent our agents as circular and also static obstacles as circular. In our multi-agent simulation loop, basically we get the velocities from the reinforcement learning framework, which give us velocity and angular velocity as action, and from this velocity and angular velocity we can calculate position in each time step to navigate the crowd. To go more further deep, our method gets learning input from the environment, and our network has has actor and critic network. So actor network basically takes an action for the agent, and critic network evaluates the action taken by the actor. Be more specific, actor network takes observation input from the environment and outputs a list of probabilities, one probability per action. And to represent the state value function, critic network also takes state observation as input and output a single value representing the state value of the state. And this method iteratively repeated for all the agents, and agents eventually learn how to navigate by different iterations. To talk about the reward function, we have different reward terms. First one is distance to goal, where we encourage the agents to reach to the goal successfully, and in case they do, we offer them a positive reward with the factor of W goal. And there could be collision in the environment, as in training environment there are multiple agents, and in case of any agent to agent or agent to obstacle collision, we offer them a negative reward with the factor of W collision. And we also have a reward term called comfort spacing. So naturally, when we walk in the street, we want to maintain a personal space surrounding us. So to emulate such behavior, we encourage the agent to maintain a certain threshold distance, which is indicated by gray area here. And in case they do or do not maintain such personal space, we offer either positive or negative rewards. Finally, we have smoothness reward term, where we penalize large deviations of velocity, angular velocity or acceleration to maintain a smooth predictive motion of the agents during navigation. And the final reward is the cumulative reward of all the reward terms. Also, we interpolated the velocity of the agent to prevent sudden accelerating. The way it works, we take a velocity, certain portion of the velocity from the agent's previous time step, and also another portion from the reinforcement learning suggested policy. And alpha is the interpolation factor here, which essentially indicates what portion is taken by taken in what ratio. And in the interaction of the environment, we basically correct any kind of incorrect navigation decision using position-based dynamics. So as there are multiple agents in the environment, there still could be agent-to-agent collision. And in case of such collision, we basically use short-range collision avoidance of the position-based dynamics, which basically corrects agent's position iteratively using geometric constraint. And constraint C here is inactive in case of there is no collision, and when there any collision occurs, constraint becomes activated, and PVD short range collision help us to correct the position from this overlapping. Sorry. And the position correction is applied for all colliding agents, and finally we calculate the velocities for all the agents. For implementation, we use stable baselines proximal policy optimization, where there is a scenario where we use 10 agents and 6 obstacles, and we randomly create start and goal position in each episode of the training. And our training takes 3.5 hours for a single policy, and we use library provided by Kwama for the preference learning part, which I'm going to discuss next. So till now we have reinforcement. We have certain parameter values we found from reinforcement learning experiment. So basically what we do, these learning parameters are from different reward functions and also other experiment. So to create believable crowd navigation, we manually tune these parameter values, and we find optimal combination to find the optimal navigation behavior, which is very difficult to do manually. So and to address this issue, we use a crowdsourced Bayesian approach to find the optimal learning parameters. So idea here is to maximize the goodness function, and goodness function here is to find most realistic navigation video. But the problem in problems related to perceptual judgment, such as crowd navigation, we cannot basically define the objective function directly, because we cannot define the how good navigation behavior by a numerical value. So we learn from relative assessment rather than absolute assessment, because we defining a navigation video is difficult by numerical value. Rather, we can present multiple navigation video to the user, and we can ask which one is better. So to generate such preferences, we conduct a user study where we present multiple simulation videos to the user, which where each individual video is basically prepared using different policies with different combination of policy parameters, and user can select one out of multiple presented video which seems realistic to them. And once we get such preference data, we normalize them to 0 to 1, and then the difficulty is measuring the goodness of the preferred data directly. And for that, we need a comparative model to represent this data set that we found from the preference survey. And we use Bradley-Terry model for that. And then we estimate the goodness values from the preferences pairs we learn from comparative preferences. And assumption here is that goodness value follow a Gaussian process, where we can see the blue denotes the potential range of values, and red are samples, which are basically different preference values. And the next sample in the Bayesian process is the value with the point with the larger value. And by iterating through our preference data, we eventually get a optimal learning parameter. And then we go back to the training again with the parameters suggested by our framework, and then we show the results, some of the results of our method. So firstly, the effect of the simulation parameter that we used in our environment. So when we use position-based dynamics, we saw that the learning is more stable, and resolving any agent-to-agent or agent-to obstacle is more smoother than when we don't use in the right side. And also when we use comfort spacing in our reward term, we can see agents are more reactive, and they always tend to maintain a certain comfort distance surrounding them compared to when we don't use in the right side. And next, the results of the user study. The left one is the most preferred policy that suggested by our framework, and we see the most preferred policy in fact gives more visually realistic video with lesser collision and smooth navigation. And mid is the mid preference, and right side is the random policy, maybe caused by any insufficient learning or incorrect combination of parameters. We also compared our method with the state-of-the-art reinforcement learning method, which is crowd simulation by deep reinforcement learning, and also some non-RL state-of-the-art method like Orca social forces. So as you can see, using our method, agents can show more anticipation in their locomotion, and other methods fail to anticipate like large dense crowd in the middle, and they just get stuck and eventually do some undesired navigational action and resolve collision. In terms of metrics, using our method, there are less acceleration, which is basically desired in crowd navigation. We always want to navigate with lesser acceleration, means lesser effort. And also in the middle, our agents takes less time to navigate to the goal. And also in the rightmost, we have more space because of using the comfort spacing compared to the baseline. Though our method can give very good believable simulation results, crowd navigation results, we still have some limitation. For example, suppose in case of extreme dense scenarios, there still could be some agent-to-agent collisions, which might be resolved using more PBT iterations, or maybe using a long-range collision avoidance where agents can avoid collision in advance. And also, we use a fixed number of 10 agents and 6 obstacles for the training scenario. If we can vary this training scenario, we might be able to learn further to get better navigation behavior. And finally, due to the constraint of training each individual policy, which takes 3.5 hours, we took a small samples from each learning parameters. So if we can include more samples from this range of the learning parameters, that might help us to get better idea of the user preference in the user survey, which might be like eventually help us to get better navigation behavior also. So in summary, we propose a reinforcement learning approach for multi-agent dynamics, and our crowd motion is realistic, both smooth and collision free, and we demonstrated it quantitatively and qualitatively. And our policy is generalizable to different locomotion scenarios. And most importantly, we simulated crowds in a manner that multiple viewers perceive as natural. Sorry. So these are the references. Thank you.
Thank you. Are there any questions in the audience? Yes, many. Yeah, maybe here. I think we have time for 1 or 2 brief questions. Are there?
Thank you for your presentation. That's very impressive. I actually have 3 questions, but maybe we don't have too much time.
Yeah,
so
we can chat
I'm curious. Firstly, I'm curious about your training time for your policy. Like how much time cost for you?
Yeah, I mentioned like around 3.5 hours for each single policy for the training in the environment. Yeah, and this might like vary if we increase, like if we vary the number of agent and obstacles, then the training time also varies. But with our scenarios where we use 10 agents and 6 obstacles, there is currently like around 3.5 hours. Yeah.
Yeah.
Thank you.
Perhaps I can ask.
Yeah, we can chat later.
Thank you. Is there another quick question?
Yeah.
So you mentioned that in dense grounds, people, or at least the particles or the agents, collide sometimes, and that might be a problem. But I don't think it is actually, because in real life, dense crowds, people usually collide. So I don't think that you need to fix that. And I would like to know more about how does your technique deals with very constrained spaces, like a narrow corridor, or for example, a narrow doorway in which people have to cross. Have you tested with that scenario?
Currently not. That's a very good suggestion. There is possibility that we can. There are always there is more scope to test on different scenarios, and your suggestion is I appreciate your suggestion. We might also test in different scenarios where we want to test the agents how they pass away to the narrow scenarios. But currently our main focus is how they react in the dense scenarios or sparse scenarios, and also how they avoid the obstacles. Yeah.
Got it. Thank you.
I think we have actually time for one more quick question. Quick one.
Thank you. This was a great presentation. I think in the reinforcement algorithm, the output was the velocity, and I'm wondering, and then you had to do velocity interpolation to make sure that the shifts weren't too abrupt. I'm wondering if you tested with acceleration being the driver, so that your acceleration just regularized with an ordinary loss function, so that it's predicting the acceleration rather than the velocity.
We did acceleration penalty in the reward function. but to make it like smoother, we use the velocity blending. Like there still could be like, though we use a penalization in the reward function, but still there could be like sudden unwanted acceleration, and that's why like we use velocity blending. Is it your question?
Yeah, I was just wondering, like for the prediction for the reinforcement learning algorithm, the output was the velocity of the agent. I'm just wondering if the output was the acceleration instead.
That might be possible, but we can think about it. But currently, like the way we designed velocity and angular velocity. Yeah. Thank you for the session.
Thanks.
Sure.
All right. Thank you very much. So let us thank the speakers again.